Now we're going to take a look at what happens if we titrate sodium hydroxide against a polyprotic acid, in this case phosphoric acid, which has 3 hydrogens that it can donate. And we're asked to look at the dominant species, or to list the dominant species at point A, B, and C of this titration. Well, you can look at this and see clearly that there are 2 equivalence points for the different concentrations. And when we look at this first area, A, obviously our dominant species at this point, before the acid has dissociated very much, would be H3PO3. So I guess our acid is not phosphoric acid, it's phosphorus acid. And at point B, our dominant species would be after the H3PO3 has donated 1 proton, so we would have dihydrogen phosphorus ion. And then at part C, after I've donated 2 of the hydrogens, I would have HPO3 2-. Now, we can use an indicator, or we could use a pH meter to do this experiment. But when you get to the equivalence point, really even 1 drop of titrant can change the pH by several units. And it's not uncommon when you first do this to just blow right past the equivalence point, because it's like learning how to drive a car. Learning how to titrate an acid or a base kind of requires some finesse. So ideally, the indicator should begin and end its color change anywhere on this rapid rise portion of the indicator curve, or the titration curve. All right, so let's take a look and see here why a certain choice of indicator might be good or not good. So in this particular question, it says methyl red changes color from red to yellow over a pH range of 4.8 to 6. Phenolphthalein changes color from colorless to pink over a pH range of 8.2 to 10. And we want to use the information in the figure below to explain why methyl red is an unsatisfactory choice, because you can look at these graphs and see, well, when I use phenolphthalein, the color change happens on the vertical portion of the curve. Whereas if I use methyl red, the color change happens too early. So I don't really have a good indicator of when I have got to my equivalence point. Now, let's do this same thought process for titration of ammonia with hydrochloric acid. Again, we can look and see, well, in the previous example, phenolphthalein was a good choice, but it is not a good choice in this case because our color change happens too early. In this case, the methyl red is a good choice because it changes color on the vertical portion of the titration curve. All right, now we're going to take an entirely different tack and talk about solubility equilibria. This is a different application of equilibrium, but it is important, and there will be questions like this on the exam. So when I talk about a saturated solution, there's an equilibrium between the dissolved particles and the undissolved solid. And we want to write a balanced chemical equation for the equilibrium that would be established for these 3 different compounds: barium fluoride, lead 2 carbonate, and silver chromate. So I can write for all 3 of these a dissolution of the solid into its component ions. And the reaction equations look like this. And it's an equilibrium. It doesn't happen a lot, but it does happen a little bit. The equilibrium constant for the process in which a solid dissolves in water is known as the solubility product constant. So instead of Kw or Ka or Kb, we call this Ksp. And we need to write the Ksp expression for these 3 reactions. So when I write it for barium fluoride, I get this. And of course, we have to remember that we have to raise all of our component parts to their stoichiometric coefficients. So I get all three of these KSP expressions. All right, it's important to distinguish between these words solubility and KSP. Solubility is defined as the quantity of solute that dissolves in water to form a saturated solution, and these units are normally grams per liter or perhaps moles per liter if we want to work in molarity. The solubility product constant is a unitless number that represents the equilibrium constant for the equilibrium between the ionic solid and its saturated solution. And the magnitude of KSP can be used to compare two solids that have similar chemical formulas in terms of their solubilities. So I've got a little insert here. Without doing a calculation, predict which of these compounds has the greatest molar solubility in water: silver chloride, silver bromide, or silver iodide. All right, now we can look at this and we could see that the highest KSP means the highest solubility. So therefore our answer will be silver chloride. Now in the next question, I've got three unlike components: barium sulfate, calcium sulfate, and lead 2 sulfate. And we want to know which one of these should have the highest molar solubility. Well, when I look at this should be calcium sulfate because, again, it has the highest KSP. They either have a common anion or they have a common cation. Now, if you're given the solubility of an ionic solid, you can calculate the value of the KSP, and now we're asked to fill in the table. So our formula and our anion and cation concentrations are going to be written there, and we can get this because we know we can write the equation and see the stoichiometry requires these to be the same. We can multiply these two together and we can get our KSP. But for silver carbonate, because the molar concentrations for silver are going to be twice that for carbonate, we have to do our math appropriately. But again, I can multiply these things together once I set up my correct KSP expression and get these numbers. At this point, again, I strongly urge you to get your calculator and do this for yourself. Make sure you can get to these numbers. For silver carbonate, for example, our KSP would be the 2.5 times 10 to the minus 4th squared, because silver has a stoichiometric coefficient of 2, times my concentration of carbonate, and that's how I get 7.8 times 10 to the minus 12. All right, now, if I'm given KSP, I can do this problem backwards. All right, so again, we can fill out the formulas, we can look at the KSPs, we can write our equilibrium expressions for all of my components, and we can come up with these numbers. I strongly urge you to stop the video, write out the formulas, write out the equilibrium expressions, and make sure you can come to these numbers on your own. We will be doing problems like this in class. We'll be having quizzes, and undoubtedly this will be on the AP chemistry exam. For example, for silver chromate, I get 1.2 times 10 to the minus 12, but that's equal to silver, which would be 2x raised to the second power times x for the chromate, and that would be equal to 4x cubed, which gives us an x value of 6.7 times 10 to the minus 5th, twice that for silver, or 1.34 times 10 to the minus 4th. All right, three things can affect solubility: the presence of common ions, the pH of the solution, which might also really be a common ion, and the presence of some complexing agent such as ammonia, cyanide, or hydroxide. Now, in the last section, you calculated the molar solubility of lead fluoride to be 2.1 times 10 to the minus 3rd molar. But in the solubility of lead fluoride in a solution that already contains either lead ions or fluoride ions should be less than that because it's a common ion. It's going to shift the equilibrium. So now we need to calculate the solubility of lead fluoride in a solution that is, we're going to do two parts. One is 0.01 molar in lead nitrate. So I set up my rice table, and I can see that my initial lead concentration will be 0.01. So my equilibrium expression is going to look like this. And when I set this up, I'm going to have 3.6 times 10 to the minus 8 is equal to 0.010 plus x times 2x quantity squared. I can make a simplifying assumption, and I solve for x. I get 9.5 times 10 to the minus 4th. And now we're going to do this in a solution that's 0.01 molar in sodium fluoride. Again, I'm going to have to set up a rice table. And I fill out my rice table with the appropriate concentrations. I set up my KSP formulation. I solve the problem, which was going to be a different kind of a problem than the previous example. And I get 3.6 times 10 to the minus 4th. Now, here's the summary. In pure water, lead fluoride has the solubility of 2.1 times 10 to the minus 3rd. My solubility in 0.01 molar lead nitrate, 9.5 times 10 to the minus 4th. And the solubility in 0.01 molar sodium fluoride, 3.6 times 10 to the minus 4th. So our solubility is going to be differ nearly by a factor of 10 between the first example and the third example. All right, the pH of a solution is going to affect this. So, for example, magnesium hydroxide becomes more soluble in water as the pH of the solution is decreased. You can think through why that is in terms of OH minus concentration and H plus concentration. And the solubility of lead fluoride is going to increase as the solution becomes more acidic. And we can explain this in terms of Le Chat. The additional H plus ions react with fluoride to form HF, and this causes the concentration of F minus in the solution to decrease, which causes the equilibrium of the PbF2 to move to the right. Now, the solubility of PbI2 is not affected by lowering the pH. Why is this true? Well, I minus comes from a strong acid. I minus can't really act as a base, so this doesn't shift my OH minus and H plus concentration at all. Now, which one of the following substances is more soluble in an acidic acid solution than in pure water? That would be nickel hydroxide. All right, all the other anions are from strong acids, so they're neutral. All right, write a balanced chemical equation for the dissolution of barium fluoride in water. Well, we've seen this before. And I can write a balanced equation for the dissociation of HF in water, and we've seen this before. Now I want to see what happens when solid barium fluoride is added to a strong acid, and I get this. All right, now I can use the values of KSP and Ka to calculate the value of Kc for the reaction written in part J, and if the value of K is greater than 1, that indicates that it proceeds spontaneously. So I've rewritten my two equations from the previous slide here, and when I do that, I can see that Kc is equal to KSP times Ka, and I multiply these two things together, I get 3.7. All right, an assembly of a metal ion and a substance known as a Lewis base, which is an electron pair donor, is called a complex ion. And we've got a lot of examples. Of course, you don't have to memorize any of these. These are just examples of some of the complex ions that you could be given on the exam, but they will give you the data and ask you perhaps some questions about these. All right, we're going to stop there. We'll have a very short video for part 5.